Hello class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 2. Today we are finishing our discussion with spontaneous reaction as we discuss Gibbs free energy and spontaneity. So the previous discussions we've had about spontaneous reactions and entropy led us to this. We've learned that in order for us to identify whether a process or a reaction is spontaneous or non-spontaneous, we need two thermodynamic quantities. One is enthalpy and the other is entropy. Today, we are combining these two. That combination actually gives us what we call Gibbs free energy. And by being able for us to by being able to identify the Gibbs free energy of a reaction or a process, we can actually identify a spontaneity. So the goal of today's lesson is for us to be able to use Gibbs free energy to determine the direction of a reaction. What do we mean by direction of reaction is whether the reaction basically favors creation of a product, which means the reaction is spontaneous, or whether the reaction favors the reactants, in which in case it's a non-spontaneous reaction. I hope you guys remember those things. We've basically discussed them from our previous discussions about spontaneous reaction. Now let's talk about Gibbs free energy. So we've talked about enthalpy and entropy, which are the two thermodynamic quantities that gives us an idea whether a reaction is spontaneous or not. Now we've discussed what enthalpy is and what entropy is. Enthalpy is basically the heat released or absorbed by the energy or by the reaction, and entropy is basically the direction of whether the molecules becomes more random, or it's basically a measure of randomness of the molecules upon during the process of reaction. If the system or has a positive entropy, we usually denote that as being spontaneous, and if it has a negative entropy, usually it means it favors the product, which means the reaction is non-spontaneous. We also talk about how in enthalpy, some reactions that releases energy or releases energy like heat, for example, burning is a spontaneous process, although some reactions that absorbs heat can also be spontaneous, for example, melting ice. So enthalpy is not enough, but we need entropy to measure whether a reaction is spontaneous. So combination of these two is basically what we call Gibbs free energy. We use the capital letter G to denote Gibbs free energy, which is the letter that we are going to use as we solve some equations and problems relating to Gibbs free energy. Gibbs free energy is named after an American mathematician and physicist, Josiah Willard Gibbs. And again, it's a combination of enthalpy and entropy that finally or ultimately gives us the direction of the reaction, whether it is spontaneous or not. This is the general equation that we use in order for us to measure Gibbs free energy. No, Gibbs free energy is basically equals to the enthalpy of the system minus the temperature that is in the system multiplied by the entropy in the system. I just want you guys to make sure to remember that the temperature that we is usually in Kelvin. Okay, so again, G is equals to H minus temperature of the system, or used in the system multiplied by the entropy. But we're going to expound more on this equation by understanding that Gibbs free energy is a state function. Like enthalpy and entropy, Gibbs free energy is a state function. What do we mean when we talk about state function is basically that we do not care on how we arrive on our product. What we care about is basically the initial and the final state of our reaction, meaning initial state our reactants and final state is basically the products. Now we do not care on how our reactants became products. Path that is a path function wherein we are focusing on the process. But for Gibbs free energy in the situation, for example, also enthalpy and entropy, we do not care on how we arrive onto the product. We do not care kung paano naging yung reactant, naging siyang product. No, we only care about these two things. We only care about the initial state of our reaction, which means the product, or which means the reactant, and we only care about the final state of our reaction, which is the product. So having said that, we can modify the first equation into something like this, wherein the change in G, or the change in Gibbs free energy, is equals to the change in enthalpy minus the temperature multiplied by the change in entropy. When we say change, it's basically the difference between the product and the reactants. If you guys have, we've dealt with a lot of these, no? The changes wherein you have the sum of all the products minus the sum of all the reactants. That's what basically is. That's why we use change, or delta. Delta G, or the change, is basically, again, the difference between the reactants and the products, wherein you have the products minus the reactants. And I want you guys to remember that when we solve for this, if the delta G is greater than zero, which means it's positive. Um, oh wait, I think, yeah, this should be, this is a little mistake when I did that. Okay, so if delta G is less than zero, meaning it is a negative, the reaction is spontaneous. If delta G is positive, meaning, yeah, meaning it's greater than zero, the reaction is non-spontaneous. So it's a little bit like how you should remember entropy, um, or enthalpy, no? But um, can also like the opposite of entropy. When entropy is positive, it is spontaneous, and if entropy is negative, it is non-spontaneous. But when we talk about gives free energy, if the delta G is negative or less than zero, the reaction is spontaneous. If your G is greater than zero, or means, which means it's positive, the reaction is non-spontaneous. I just want you guys to remember that. And then we can further modify this equation right here, this equation on top, in order for us to give a more standard way of measuring the delta G, no? Because especially if we have temperature, the temperature must needs to be constant, as well as pressure needs to be constant. Otherwise, your delta G will always be changing. So what we need to do is create a standard condition wherein we have a consistent or constant pressure of 1 atmosphere and constant temperature of 25 degrees Celsius. 25 degrees Celsius is basically 298 Kelvin, which is the temperature that we use in these reactions to measure delta G. So using this standard condition, we can measure what we call the standard free energy change. So this is a free energy change, or delta G, a change in free energy. But by adding a standard condition of 1 atmosphere and 25 degrees Celsius, a more standard condition, we can create a standard free energy. And this is the equation that we have to use in order for us to measure the standard free energy change, meaning this is the delta G at 1 atmosphere and 25 degrees Celsius in the reaction. We can also measure the standard free energy change by using the standard free energy change for formation. So this delta GF here, right here, is basically what it is usually given. These are pre-measured delta G measurement of elements and molecules. No, it is usually given to you in table. You just have to take them and use the equation in order for you to solve delta G. So what do I mean by that? Let me show you an example here. So here, consider the dissolution of, this should be silver. So much typographical errors. This should be silver. Consider the dissolution of silver chloride or AgCl and determine its spontaneity. So we have silver chloride here and we are basically dissolving it. We are separating the silver and chloride by adding water into it. So that's why making it an aqueous solution from solid to aqueous solution. So we are basically dissolving the two, separating the silver from chloride. And the delta G formation, or the standard free energy change of formation for each of these molecules and elements, is given in the table. So using the equation that I showed you earlier, you can measure the delta GF, delta G, or the standard free change, yeah, the standard free energy change of this reaction. And by solving this, we can identify whether their reaction is spontaneous, or whether this reaction is spontaneous or not. Again, remember, we have to use this because we want to have a constant atmospheric pressure, or constant pressure, and basically constant temperature. No? Otherwise, if these keeps changing as the reaction continues, we will have varying delta G, and that is no good if we want to determine whether the reaction is spontaneous or not, because pressure and temperature changes how the reaction proceeds. No? So let's redo this. So this is basically our given na. We just have to also consider that the other given is basically each of these has one mole, no? Because we have one, and one there, no? Those are the coefficients. So we have 1 mole of each reactions. Okay, so let's measure this up. So what basically, so this is our given. I'm gonna write our given here. And then what's asking us is basically the delta G, or the standard free energy change. And then the equation that we have to use is delta G, standard delta G is equals to the sum of the delta G of formation for products minus the delta G, or the sum of all the delta G of formation for the reactants. Okay, and then let's go ahead and solve this problem here. Solution. Just gonna underline this. There you go. Okay, so we know that the delta G, or the standard free energy change, is equals to the sum of all the delta G of the products. We have our products, so this is basically the sum of the delta GF of Ag, or silver cation, plus the delta G of formation for chloride and iron, minus, yeah, basically minus the delta G of formation for silver chloride. And then we can just plug in the numbers. You also have to remember the um, coefficients. So that each coefficient has one, so which means each of these has 1 mole. So what we're going to do is, for the silver cation, we have 1 mole, multiply the delta GF of AgCl, which is negative, or Ag positive, Ag cation is 77.1 kilojoules per mole. So we have 77.1 kilojoules. Remember this, guys, this is in kilojoules, so meaning this is 7,700 1 or 710 joules, no? So it's in kilojoules, remember that. We have per mole plus the delta GF of Cl minus. Cl minus also has 1 mole, so we have 1 mole of chlorine and iron, and the delta GF of chlorine and iron is negative 131.3 kilojoules per mole. Okay, and then minus, as for the product, we have 1 mole of our product multiplied by the delta GF of our product, which, or reactants, sorry, not product, reactants, silver chloride, which is 109, negative 109.8 kilojoules per mole. Okay, and then the moles are cancelled, cancel all the mole, and what you're left with is basically kilojoules, and just plugging that in the calculator you would get 55.6 kilojoules, or this is basically equal to 5560 joules. So this is the free energy of change, the standard free energy of change at 1 atmosphere at 25 degrees Celsius. And since this is positive, you can see this is positive, delta G means the reaction is non, or yes, the reaction is non is spontaneous. What do we mean by that is it favors the reactants. And when it favors the reactants, it means AgCl or silver chloride does not easily dissolve. No, if you added AgCl in water to dissolve it, it doesn't usually dissociates. It doesn't. Ag and Cl does not easily dissociate. So we usually would have more reactants than products in this case, because we have especially in this case of quite big delta G. So I hope that is clear. So um, I hope if you guys have any questions, just message me regarding this problem. But I hope it's clear on how to measure it and how we arrived to this solution and how we arrived to this equation. Again, this is just one of the equations that you can use for delta G, or the standard free energy of change. There's another equation wherein we include the temperature itself, but it's usually given when we have enthalpy and entropy. Since remember, Gibbs free energy is a combination of enthalpy and entropy, sometimes we have equations wherein they give us enthalpy and entropy. No? So this is the enthalpy and this is the entropy. So for example, the sample problem, determine the spontaneity of the dissociation of ammonium nitrate, or NH4NO3. NH4 is ammonium, NO3 is nitrate, the compound used in cold pack. Interpret the values obtained from the calculations. So this is your chemical equation here. This is the chemical process wherein you have solid ammonium nitrate, and it dissociates to nitrate cation, or ammonium cation and nitrate and ion. So when we are given a table wherein they give us the standard enthalpy of formation and the standard enthalpy of formation, and standard entropy, what we're going to do is we have to measure each separately and then combine them both. Or you can also just go ahead and write the whole quite a big equation, no? But let me show you. So this is basically you're given right here But also, as you can see, we also have 1 mole of each reactants again. So remember, if they have coefficients, use the coefficients as the number of mole, because that's basically how much moles of that product or reactant you have during the chemical process, or during the chemical reaction. And what they're asking us is basically the spontaneity of the reaction, meaning basically delta G. And the formula that we have to use is basically the delta G, the standard free energy change is equals to the standard enthalpy of change minus the temperature multiplied by the standard entropy of the reaction. So for the solution, what you want to do is start with, para hindi tayo nalilito, no? You can start with the delta H, or the standard enthalpy of change with this equation, and it's usually given. And you can use this by still using the same equation of basically delta H is equals to, you have the sum of all the delta H of formation for products minus the sum of all the delta H formation of the reactants. So what you're going to end up having is basically equals to, uh, you have your products as NH4 and NO3, so you would have delta H formation of NH4 positive plus the delta H of formation, the standard delta H of formation for another product. You have NO3, which is nitrate, and then minus, you have your reactant, which is ammonium nitrate, so you have the delta H of formation for ammonium nitrate, NH4NO3. Then what's gonna happen is you have delta H is equals to, it's kind of long, again you have 1 mole multiplied by the delta H of formation for NH4 positive, which is right here, negative 132.5. 132.5, you would have kilojoules per mole plus, you have 1 mole of NO3, and the delta HF formation of NO3 is negative 207.4 kilojoules per mole. And then you would have minus the product, which is, again, you have 1 mole of the product, and the delta HF of the product is negative 360 or 365.6 kilojoules per mole. And then you can cancel all the moles, and then combining all the equation and the calculator, you would get that the delta H of the delta H standard enthalpy of change, for this reaction is equals to 25.7 kilojoules, because the moles are cancelled, you're left with kilojoules, and this is equals to 25,700 joules. Okay, but we're not done yet, we only have one. The second part that you have to do is solve for the entropy, and you have to use the same equation wherein you have the sum of all the entropy of the product minus the entropy of all the reactants minus the sum of all the entropy of the reactants. And then if you rewrite the equation, you would end up having, again, you have 1 mole, but basically let's write it this way so I can, so you know what is happening. So you have delta S 4 NH4 plus delta S of NO3 minus the delta S of NH4 NO3, and you would have basically again 1 mole multiplied by 113. This time it's joules per molar Kelvin plus again 1 mole multiplied by 146.4 joules per molar Kelvin, and then minus the product, which is you have again 1 mole of the product multiplied by its delta S, which is 151.1 joules per molar Kelvin. As you can see, we can cancel the moles because one it's in the numerator here, it's in the denominator here, and what you're left basically is actually equal to 108.3 joules per Kelvin. Okay, so now you have your delta H and you have your delta S. Now for number 3, you can proceed with solving delta G. And we know delta G is basically delta H minus temperature delta S. And since this is the standard, this is where it is important to use a standard, because in standard we have 1 atmosphere at 25 and 25 degrees Celsius. 25 degrees Celsius, okay, let's just focus on the temperature. But remember, this is at 1 atmosphere, no? But this is, since this is standard, that's why we have our degree there. If you see the degree, this means this is standard, wherein we use 1 atmosphere and 25 degrees Celsius. 25 degrees Celsius is actually equal to 298 Kelvin. Just remember that. Now we can solve for delta G, which is 25,700 joules minus the temperature, which is 298 Kelvin, multiplied by the delta S, which is 108.3 joules per Kelvin. Okay, you can see now why you need the Kelvin, because you can cancel the Kelvin, and what you're left here is basically negative 6,573.4 joules. And since this is negative, delta G means this reaction is spontaneous, meaning it favors the formation of the products. So as you can see here, if you use this equation, the things that you have to remember then, that in order for the delta G to be negative, it means that one way delta H should be negative, or that the temperature is high enough in order to make your delta G negative. Because in a spontaneous reaction, delta S is usually positive, no? So when you have negative delta H, uh, it means it kind of helps with having a negative delta G to make a spontaneous reaction, or at least you should have a very high temperature in order for the reaction to become spontaneous. So I hope that is clear. That is all the lesson for today about Gibbs free of energy. It's basically the same. We've used the same equation uh, from the last time when we were solving entropy. Uh, but yeah, this is just a combination of enthalpy and entropy. And if you guys have any questions, please do not hesitate to message me. Thank you so much and have a great, guys, have a great day.